Today, what I want to do is talk about immunity a little bit broadly to introduce it, and then next week we'll talk about more of the specifics of immune function. Now, to do this, I have some stuff already set up in this presentation software that I've used in the past. So I'll go here, and really what I want to cover today is just in what's on the screen here. And when we took a break, I wasn't looking at the clock correctly. It's kind of hard for me to read the big hand, the little hand, and talk at the same time, apparently. So I thought we would have less time. So we should be good. Now, what I want to do to begin with, where it says immune function at the top here, is I just want to sort of give an overview of what immune function is and what we're going to be concentrating on next week. And then the bottom part there, know your enemy, I want to talk a little bit about what it is that our immune system is protecting us from. So to begin with, just I kind of said, wait, did I? I think I said this, that the lymphatic system and immune function don't completely correspond. And this sort of gets at that. The lymphatic system is an organ system, okay, like the other organ systems we looked at. But the immune system is a functional system, which means that it's not based on a specific subset of organs in your body. Components that lend themselves to immune function are across multiple systems. In fact, all systems of your body have some part to play in immune function. For example, we're going to be talking quite a bit about white blood cells. And so obviously they're a component of blood, which is the cardiovascular system. And they are going to be moving through the blood vessels. So there's cardiovascular transport there too. Now we've talked about the lymphatic organs, and they have a lot to do with immune function. We'll see that quite a bit. And then the next thing, dendritic cells, is not a particular organ or necessarily from a particular system, but it's a representation of how there's immune components throughout the body. Dendritic cells are something that we talked about in A&P1. When we're talking about the skin, in the stratum spinosum of the epidermis, there is a particular type of cell called the cell of Langerhans, which is the dead white guy name for the cell. More appropriately, that we should call them dendritic cells. The dendritic cells in the skin are cells of Langerhans, but there are dendritic cells elsewhere in the body. In all mucous membranes, there are also dendritic cells. They're just not called cells of Langerhans. And what they do is they basically hang out in those tissues, which are barriers. Anything that's outside your skin or on the apical side of a mucous membrane, immunologically, is not going to do anything to you. It has to get past one of those barriers into your body to cause disease. And dendritic cells are all hanging out in those locations. And it's not until they get past the mucous membrane or the skin that pathogens can have effect. So those cells are hanging out there to alert the rest of your immune system to the presence of pathogens that have gotten through barriers. Yeah.
Is that in the dermis?
No. I just said that dendritic cells in the skin are in the stratum spinosum, which is one of the layers of the epidermis. Now, actually, in the chapter, they talk a little bit more about dendritic cells, and they are a specialized type of white blood cell, which is not in the blood, but that's where they come from. Okay. And then at the bottom of this list, I put interstitial fluid, which is sort of the basis of explaining what the lymphatic system does. It drains excess interstitial fluid from everywhere in your body. So anywhere that you have interstitial fluid, there's going to be some aspect of immune function taking place. And you have interstitial fluid everywhere in your body. All tissues have interstitial fluid. Therefore, all tissues play a role in immune function. Not with every single immune response, just when an immune response is necessary there. But in connective tissues, which is largely where we see interstitial fluid, there are mast cells, which are important for the inflammatory response. There's usually white blood cells, like plasma cells and those sorts of things, are found in tissues too. So they're always there, ready to be part of an immune response. And then I want to make sure that you understand that the immune system works as an integrated whole. And I'm saying that because we have to study it in its component parts. And I'll explain those component parts in a second. But we're breaking it down so that it's in bite-sized pieces, so to speak, to understand the different components. But we have to understand that everything's working together. And at the end of talking about this, we'll sort of end with a summary figure that puts it all together and how the different components all play a part. When you have an immune response, the same things always happen. They stop happening once that immune response is useful. So sometimes we think of, one thing's always responding and other things only respond under certain circumstances. But really, given the chance, the immune response will run all the way out, but it will stop once there's no longer a pathogenic threat or something like that. Or once whatever part of the response has been effective in handling things. But it is always one integrated and all-encompassing, that's not the word I wanted, but a response. And we'll see that, I'll remind us of that at the end of all of this, which is at the end of next week. Now, the bite-sized chunks that we're actually going to be looking at are somewhat represented in this picture. This is a picture out of another book, and I don't know that there's necessarily a picture like this in our book. And all it is it's a flow chart or a family, not a flow chart, but a branch structure just showing different parts of things. And really all that I want to get out of this, as far as talking about the parts of the system, is that there's innate immunity and adaptive immunity. And so next week, basically, the first half, we're going to talk about innate immunity, and the second half, we're going to talk about adaptive immunity. In this picture, they don't quite break down innate immunity any further. They just have this little box saying, essentially, it's what's there when you're born. Within adaptive immunity, they break that down into active and passive, which would be something you could say about innate immunity also. There are passive and active components of that. For example, your skin is a barrier that things can't get through. That's not an active component in that you don't have to expend energy for that to block the entry of pathogens into your body. And you're born with it. So that would be like passive innate immunity. Not that that's a formal term for anything. And then active immunity means things that you're expending energy on. And in innate immunity, you're born with certain types of white blood cells, like macrophages, that are part of the immune response. And they require energy to do their job. So that would be an active thing. So we could kind of say within innate immunity, there's an active and passive component too. But with adaptive immunity, what it's getting at is a little bit different. And I do want to talk about this here because it's probably something that you're somewhat familiar with just from common experience. Adaptive immunity is your body's ability to respond to specific pathogenic threats. It's based largely on antibodies. Now, it's actually based only partly on antibodies, but other molecules that are like antibodies, which we'll talk about when we get to them later on. So you adapt to your environment by developing antibodies and similar molecules that can recognize specific pathogens. So in what we have on this board here, active immunity is defined as what develops in your body in response to a specific exposure. And then passive immunity is what's produced outside of your body, meaning by a different source, and introduced to your body to help fight off a pathogenic invader, whatever. And then within each of these, they have naturally and artificially, or naturally induced and naturally acquired and artificially induced versions. And I just want to mention this, kind of paints a picture a little bit. Passive immunity is basically when you're fighting off an infection with antibodies that somebody else made. That's essentially what it means. The naturally acquired version of that is that when you were first born, you did not have a functional adaptive immune response. So you used antibodies that your mom made. So in the little box there, it says it's transfer through the placenta and breast milk. So fetal circulation is really just getting blood components from the mother. So any nutrients and those sorts of things are coming from the mother. Any waste is expelled through the mother's circulation. And in that, any antibodies that the mother makes get transferred to the baby. So when the newborn first arrives in the world, it's ready to fight off anything that the mother is immune to. Okay. It says breast milk there too, because it's possible that the mother will be exposed to something pathogenic after giving birth, but before the newborn has developed its own adaptive immune system. And so there's a mechanism for transferring antibodies through breast milk too, in case a situation like that crops up. It's probably not that common. And I say that because there are certainly situations where newborns don't get mother's milk, okay, whether they need to get formula or whatever it might be. So the primary naturally acquired passive immunity comes from placental transfer, but there's a mechanism to continue it during the first 6 months or so of the newborn's life when it doesn't have its own adaptive immune response. Artificially induced passive immunity is when you have antibodies introduced, usually therapeutically. The best example of this is a snake bite kit. So snake venom toxin is going to be lethal, I suppose, depending on the species of snake. But let's pretend we're talking about just poisonous snakes. Your immune system can adapt to a threat like that, but it takes a couple of weeks. Okay? And you're not going to survive a couple of weeks after a snake bite from a venomous snake. So snake bite kits have a little ampule of anti-snake venom toxin serum. And it's an injection you give, or I don't know exactly how it's delivered, but basically it gets antibodies into your system that would bind to the snake venom toxin. They were made by somebody else. And by somebody else, I might mean, a rabbit or a pig or a goat or something like that. Whatever it is, it's an antibody that will recognize snake venom toxin. So you immediately are immune to that because you've gotten the antibodies from another source. That's artificially induced. There are other therapeutic uses of antibodies that would fall in that group there also, but the snake venom toxin thing is a good example of it. Now, active immunity is when you make the antibodies yourself. And naturally acquired active immunity is when your immune system learns of the presence of pathogens in your environment and you develop an immunity against that. Usually what happens is you get sick, you fight that off, the symptoms go away, and then you won't get sick again because you've developed an immunity to that. Like chickenpox. You get exposed to chickenpox once, you get sick, you get pox, and then you fight it off, you come through, and after that, you're not going to get chickenpox again. Yes, there are rare situations where it happens twice, and I'm not going to get into that here. But generally, once you've been exposed to chickenpox, you're immune to chickenpox. And that's the naturally acquired active immunity. Artificially induced active immunity is basically vaccination. So I use chickenpox as an example because I have some personal experience with that. I've never had chickenpox. When I went to college, and I'm sure all of you had to do this too, you had to provide immunization record. Okay. So because of when I was going to college, there was no such thing as, or I should say when I was born, there was no such thing as a chickenpox vaccine. But by the time I went to college, it had been discovered, developed, invented, whatever. And so I had no record of having been immunized against it. I think I might have actually had blood work done, and they did a titer, and I had no naturally occurring immunity against chickenpox. So I had to get the chickenpox vaccine. And so I've never had chickenpox, but I actually am immune to it because I've got this artificially induced immunity. The vaccine contains non-virulent chickenpox virus in it. So it's not going to cause chickenpox, but it's still going to activate the adaptive immunity, and I'll develop an immunity to it. But if I have ever been exposed to chickenpox since then, I don't have to worry about it because I have that immunity as if I had it as a child. Yeah.
A lot of vaccines, they just contain like the protein coding on a lot of viruses that are in the capsid.
Right. So a virus is just genetic material surrounded by proteins. The proteins by themselves are not virulent. That's just the container. It's the genetic information that's bad. So if you're going to make a vaccine against a virus, what you'll often do is take the genetic material out of a virus, and all that's left over is the proteins. You develop antibodies against those proteins, and therefore you're immune to the virus. Now, you've probably heard of the chickenpox vaccine, but it's not usually referred to specifically as that. More often, you'll see it referred to as the shingles vaccine. So if you're driving down the road, you're going by CVS or Walgreens or something like that, see a sign saying, get your shingles vaccine. That's what it is, chickenpox vaccine. And it's probably advertised like that because shingles is a concern of older Americans who have money to spend to get the vaccine at the drugstore or whatever. But what shingles is it's really a reoccurrence of chickenpox. When you get chickenpox for the first time and you develop your naturally acquired immunity to it, you have fought off that infection and the symptoms go away. But you haven't actually gotten rid of the chickenpox virus. Chickenpox virus ends up hanging out in nervous tissue, usually in dorsal root ganglia. And then sometime later in life, you might be exposed to some sort of stress, and by that I mean another illness or anxiety or good old-fashioned stress. And that'll sort of activate those chickenpox viruses again, and they'll move from the dorsal root ganglion along the spinal nerve that dorsal root ganglion serves, and move out to the skin. Okay? And the connection between dorsal root ganglions and your skin is very topographical, which is to say, this dorsal root ganglion right here is connected to this skin right here. It's a band across your body. So shingles is kind of like chickenpox just in that area. It's not exactly the same lesion as chickenpox, but it's the same virus causing problems just in that area. If you've had chickenpox before, then you are susceptible to getting shingles in the future. If you've never had chickenpox, you won't get shingles. You can't get shingles without having had chickenpox before. So if you fall into that group, you've never had chickenpox, you get the shingles vaccine, you're really getting the chickenpox vaccine so that you never get chickenpox and therefore can never get shingles. But if you've had chickenpox, the vaccine doesn't help because you've already got the virus in your body and you are going to be susceptible to shingles. Yeah.
I think I'm going to ask what you just said, but just so I get it. If you've had, because I'm in the same situation, I never had chickenpox. I never got vaccinated until it was like last year.
Mm-hmm.
So I can't get shingles, but someone who had chickenpox can get shingles.
Right.
Okay.
So you've been vaccinated against chickenpox because you never had it before and you got the artificially induced immunity to it. And so that means that you don't have chickenpox virus, an active form of chickenpox virus in your system, hanging out in the peripheral ganglia to someday express itself as shingles. But somebody that has had chickenpox and therefore doesn't have to get the vaccine for immunization records for college could potentially get shingles in the future. And they can't get the shingles vaccine because it's not effective to somebody that's already had chickenpox. And if you are driving along and you had chickenpox as a kid and you're worried about getting shingles as an adult, and you see, get the shingles vaccine, you pull into CVS, you say, I want to get the shingles vaccine. First thing they'll ask you is if you had chickenpox. Say yes, and say, sorry, can't help you.
So I'm sorry. If they won't vaccinate, I previously worked at a doctor's office, and we vaccinate people with the shingles vaccine who are over 50, 65 years old, and we don't ask if they've ever had chickenpox.
Okay, then some of them are paying money for something they don't get.
I have no idea. That's why I was so confused when you were just saying all that, because I didn't know.
Okay.
So $250 for nothing.
I've never gone in to ask for the shingles virus because I know I don't need it.
And they literally make everybody try to get it.
I assumed that that meant, that they would check that first. Possibly they don't check because self-reporting from patients is one of the least reliable data sources in medicine. So they might say, have you ever had chickenpox? Yeah. They might say, yeah, I think so. And really they remember their little brother getting chickenpox.
Yeah.
So they don't get the vaccine. So I suppose to some degree it's better to go ahead and get the vaccine when you don't need it than not get the vaccine. But if you know you are immune to chickenpox, whether you had it before you've had the vaccine, you don't need to get the shingles vaccine. Yeah.
So in virology, you have lysogenic and lytic cycles. So does stress?
No, I don't know that. I'm not an expert in virology. I can't answer that kind of question.
I was just going to wonder if stress induced kind of the lytic cycle within the dorsal root ganglion.
I have no idea. It's not my area of expertise. Sorry. Go find Professor Machaziak. He is a trained, I don't know if virologist is correct, but he got his Ph.D. in, I think, immunology. So he could definitely answer this kind of questions. I don't know, I'm not an expert in that field, so I can't really say anything beyond that. See, one last thing I want to say about that. The worst case of shingles I've ever heard of, kind of amusing, unfortunately for the guy that got it, but my next door neighbor, Bob, I didn't see him for a little while, a few weeks. And it might have been like the end of winter, beginning of spring, or something like that. And so it didn't really occur to me that I hadn't seen him because he usually doesn't come out in winter. And then I see him out doing yard work. I might have been raking the yard or something like that in preparation for yard work. And he comes out and I see him and he's lost a bunch of weight. And so I say, Bob, you look great. What'd you do to lose all that weight? He says, you've got shingles. He got shingles in his throat, okay? Not on his neck, but in his throat. I described it as being in the dorsal root ganglion. It doesn't have to be the dorsal root ganglion. It could be any ganglion. And so he must have gotten it in a ganglion associated with either the hypoglossal, glossopharyngeal, or vagus nerves. Those are nerves that are connected to the soft tissue of the throat. So he got shingles where those nerves are connected, which happens to be in his throat. And because of the swelling associated with that and the irritation, et cetera, he couldn't eat. So he lost a lot of weight thanks to the shingles. And I just loved his response to that. I found it very amusing. It's horrible. I felt really bad for the guy, but he's stoic. He didn't really seem to be too bothered by it or anything like that. So the next part I want to address here is it says know your enemy. When I talk about the immune system, I'm usually using military or police metaphors. Okay? We have foreign invaders, we have cells fighting off infection, dendritic cells are sentries, we have attack cells, we have defensive barriers, all those sorts of things. So I want to introduce you to the enemy. And primarily the enemy that we're talking about are pathogens. Now, really, immune responses are going to be for infections and tissue damage and internal diseases like cancer or something like that. So not everything is about pathogens, but I do want to kind of illustrate a lot of this about pathogens because that's kind of what we focus on for this section of the course. So the word pathogen is made up of two parts. The root, pathos, comes from the Greek that means disease or suffering. And then gen comes also from the Greek, and it's a root that basically means to be born, as in the word generate or genesis or something like that. So when we see the word pathogen, we're talking about things that generate disease or generate pathos. We'll see a number of other words that have a similar kind of construction. In fact, we've already met one, antigen. Okay. Antigens generate antibody responses. They don't generate antibodies, they generate antibody responses. And then there's allergens that generate an allergic response, or carcinogens that generate cancer. So when you see this kind of construction for a word, that's what it's getting at. But I want to talk about pathogens. Now, for pathogens, or these infectious agents, I want to talk about a number of different types. The first type is bacteria, and that's going to be our primary example of a pathogen. In the book, there will be all sorts of references to pathogens and foreign invaders or whatever, microbes, that are kind of vague on what exactly they're supposed to look like, but it's usually some sort of a representation of a bacterium. Okay. It's not the only thing that causes infection, but that's usually our go-to example. Bacteria are interesting because they're a different form of life completely. Living organisms fall into two major categories. There are prokaryotes and eukaryotes. Karyo, in both of those words, refers to nucleus. And this is a Greek word, so the prefix pro in Greek means before. So prokaryotes are organisms from before the nucleus, meaning that they existed long before any organism started having a nucleus in its cell. Which really means that they're just cell membranes with cytoplasm in them and not a whole lot of specific structure to them. They have DNA, but they don't have nuclei. They have ribosomes, they have cytoskeletal proteins, but they don't have mitochondria or Golgi apparatus or endoplasmic reticulum or any of those membrane-bound organelles. Okay. Those are prokaryotes. Eukaryotes, the word translates to true nucleus. That's going to be everything else, things that do have a real nucleus. And with nuclei, those cells are also going to have other membrane-bound organelles, like mitochondria and Golgi apparatus and endoplasmic reticulum and peroxisomes and lysosomes and vesicles and vacuoles and all that stuff. That's what eukaryotes are. What's important to understand what's going on here is basically prokaryotes are structurally very simplistic. There's basically three shapes that bacteria come in. What's on the board here is a rod-shaped bacterium. There are also spherical-shaped bacteria and spiral-shaped bacteria. And I have a picture of rod-shaped bacteria because that's the most common, especially in relation to the pictures we're going to see. On the other hand, eukaryotic cells are very complex and diverse, structurally speaking. I just described the three types of bacteria. Looking at our own cells, we can come up with many more than three types of cells. Okay, skin cells, neurons, muscle cells, they're all structurally very different. Okay. So with the advent of the nucleus and the development of eukaryotic cells, we start to see much more diversity and structure of cells. Usually diversity sounds like a code word for more advanced or more evolutionarily advanced, whatever. And you'll often hear people referring to bacteria as being evolutionarily old and eukaryotes as being more advanced. I don't think that's entirely true. That might be relevant in terms of structural differences, but functionally, bacteria can be as complex, if not more complex, than eukaryotes. And by functionally, I basically mean metabolically, the chemistry that takes place. That's about all that happens inside a bacterium, is a bunch of chemical reactions that are catalyzed by enzymes and that sort of thing. But bacteria have the ability to live in environments where eukaryotes are not capable of surviving. And from that, it kind of says that, maybe they are more complex organisms in that they've found a lot more different kinds of environments to populate. I can almost remember, right sort of at the beginning of my education, when it was discovered that there are bacteria living at the bottom of the ocean. So in the ocean, there's part of the water that sunlight can diffuse through a little bit. And then eventually the sunlight can't diffuse any further. And so we switch from that first area, I can't remember what it's called, the life zone maybe or something like that, to the midnight zone. And then eventually it gets down to what's called the dead zone, which is so deep that nothing gets in. Pressure is incredibly high. Many of the molecules we associate with life, like oxygen and those sorts of things, are not present in the concentrations that we associate with living organisms. But somebody discovered bacteria that live at the very bottom of the ocean. And they're chemically very different from a lot of different organisms because they have to deal with this different environment. They get their energy instead of ultimately from sunlight, instead from heat that's released by hot air vents in the floor of the ocean, which really means heat from magma below the crust of the earth being released up into the sea. And from that heat, they're able to catalyze a lot of important reactions to develop energetic molecules that can use. Like we get ATP ultimately through photosynthesis, and not directly. ATP is made from glucose, and glucose is made through photosynthesis. These bacteria do something on their own using that heat energy rather than light energy. So that, I think that was discovered in the 70s or something like that. So I can almost kind of barely remember that.
Yeah, they actually taxonomically separated them.
Yeah, I don't want to get into taxonomy here. So. Yeah, they fall into a group called extremophiles, which, because they live in extreme environments, but they're prokaryotes, essentially. And I'm telling this kind of to illustrate just the amazing aspects of life. They can live there. They can live deep underneath the Arctic or Antarctic ice. They can live kilometers deep in the soil. There's bacteria that have been found 6 kilometers deep in the soil. So they're nowhere near sunlight. They're nowhere near oxygen. And they get their energy from radioactive materials in the soil. There have been bacteria found in space. Now, I don't mean alien bacteria. I mean actually Earth bacteria that were launched into space by some sort of meteor impact far, far in the past. And when those rocks come back down to Earth, those bacteria are viable still. They probably weren't alive in space. They probably were in sort of a hibernation state, but they exist. Now, part of telling you all this is because I think it's really incredible all the different things that life can do, which makes things like Mars rover missions really kind of exciting because let's see what they find there. But really, in terms of what we're interested in, these extreme condition kind of organisms don't really matter to us because the bacteria that are pathogens for us are adapted to our internal environment. They like a pH of about 7.35, a ambient temperature of about 37 degrees Celsius, a nice water-based solution to live in, access to nutrient molecules and oxygen, that sort of thing, and the ability to get rid of waste molecules like carbon dioxide or methane or whatever it might be. Okay, they're adapted to our internal environment. Those extreme organisms that I mentioned, more out of a sense of wonder than anything else, don't really apply here because those kinds of things aren't likely to cause an infection, because they wouldn't survive in our body because they're adapted to some other environment. Okay. So I don't actually know specifically what type of bacteria this is, but it is a rod-shaped bacterium. I want to point out down at the bottom, there's a scale bar here that's 1 micron long. So this particular rod-shaped bacterium here is probably about 2 microns long and maybe 1/4 of a micron in diameter. How big is the average cell in your body? Or can you tell me the diameter of a cell in your body that we've talked about in this class? There's definitely been some that we've said specifically. Well, yes, but I want something more specific as size. That's very, very tiny. But what's the average diameter of a red blood cell? I'm so ashamed. I've told you this. It's about 8 micrometers. Okay. This picture here is probably about 8 micrometers wide, maybe 6. So a red blood cell would completely enclose everything that's in this picture. Okay. Just to give you a sense of scale. Now, like I said, I'm sort of showing you this because bacteria are going to be sort of our go-to example of pathogens. But another type of pathogen I want to talk about are viruses, and I've already talked a little bit about them. Now, viruses are different. They are not organisms. Living organisms, whether they're prokaryotes or eukaryotes, have to satisfy certain criteria to be called living. One of those criteria is that they have to be able to reproduce on their own. Viruses cannot reproduce on their own. Okay, so they're not living organisms. Lysol commercials drive me crazy. Lysol does not kill viruses. You can't kill something that's not alive. It will potentially destroy them, sure. And maybe kill is just meant to mean destroy, but it doesn't kill it because killing implies that they're alive to begin with. The way that viruses reproduce is that they infect a host cell and exploit that host cell's ability to make new nucleic acids or proteins. Okay. And because of that, that's why they're pathogenic. They'll infect a cell, take it over, force it to make new viruses at the expense of the cell. The cell's going to die because it's been infected by viruses. Now, a lot of the cells that are infected by viruses and a lot of our common viral infections are epithelial cells, like the influenza virus, whether it's the respiratory influenza or the so-called stomach flu. Those are infecting epithelial cells. And epithelial cells get replaced very easily. So when they're infected and they die because of the infection, new ones are going to be made and you'll recover from that fine. But there are other cells that succumb to viral infections. For example, HIV infects a specific type of white blood cell. And HIV causes acquired immunodeficiency disease, syndrome? Yeah. Because these types of white blood cells die off because they're being forced to make viruses. And so white blood cell count drops and people are more susceptible to common infections like pneumonia or something like that. Now, the really insidious thing about HIV is it infects a cell, it takes it over, it basically fills the cell up with new viruses until the cell bursts open. And what's really kind of scary is when that happens, the viruses sort of hold on to a little bit of the white blood cell membrane, wrap that around them, so the immune system thinks that that virus is just one of your white blood cells because it has an outer coating that is basically, a fur coat made from that white blood cell. And that's why it's one of those really kind of insidious sort of infections. Now, there's not a scale bar on this picture, but these virus particles are about 80 nanometers across, okay? A nanometer is 1/1000th of a micrometer. So 80 nanometers is 0.08 micrometers. Okay. So going back to this picture here, the scale bar, that's 1,000 nanometers. So 80 nanometers is just a little fraction of the beginning. Okay. So while this picture represents stuff that could probably all fit within a single red blood cell, this picture represents stuff that all fits within a single bacterium. And the scale here is actually a lot smaller. That picture before would probably be covered by a single white red blood cell. This picture would fit inside of one of those bacteria, and it's probably not even quite the diameter of the bacterium, and it's far from the whole length of the bacterium. So these are very, very small things. They are simply just a protein capsule that contains some sort of genetic material. So like we were talking about earlier, a vaccine is really just the protein outer coat part without the genetic material in the middle. And you acquire immunity because you develop antibodies that recognize the shape of the protein. And so if you, shape of the protein. So if you are ever exposed to the actual virus, you're immune to it, and its genetic material won't ever be able to get in and infect cells. So that's where the vaccine comes from. This is a picture of a fungus. I got this picture from a website that doesn't exist anymore, but it was a really cool website. It was a army.mil website, mil for military. And basically what it was is this long website with all sorts of examples of what you would see under the microscope of material collected from urinalysis. So this is some sort of fungal infection that you would see in urinalysis. The most common fungal infection that you'd associate with urinalysis is a yeast infection, and I doubt this is yeast. The reason I doubt that is because I don't think yeast has this very branched pattern to it as the cells come together. Yeast is a single organism, and it's probably would look more like one of these little things off here. This might be a yeast cell right here. I don't know. But I picked this one because what I wanted to represent for the fungus is that fungi are sort of their own sort of organism. They're eukaryotes, but they have some characteristics that we see in animals and some characteristics that we see in plants. So I picked this because it kind of looks like a branching pattern like a plant, but it's a fungus. Okay. We're not going to talk about fungi necessarily here, just to understand that there are certain pathogens that fall into that group. What we do to deal with fungal infections isn't terribly different from what we do to deal with bacterial infections, other than the drugs we use. We have specifically antifungal drugs as opposed to antibacterial drugs. But in our body, some of the systems, some of the immune response is kind of the same for both. And then the next section is what are parasites. Now this picture, I actually don't know what this is, and I could probably do an image search for it, but I haven't yet. I really just picked it because I thought it was a cool looking picture. I think this is a single-celled organism. It looks like these are cilia and these are flagella, or it could be a multicellular organism, and this is sort of like its mouth, and I don't know what it is, but it's a parasite. Parasites can be either single-celled or multicellular organisms. This is an example of a single-celled organism. It's the amoeba. I picked this for a couple of reasons. One, you can see its nucleus very clearly. This is a eukaryotic organism. Okay, and then the rest of the texture we see in the cell are other organelles that are in it. So some of these might be mitochondria or vesicles of some sort. All the little dots might be ribosomes that are on the endoplasmic reticulum. I don't know, but there's a lot of texture because there's a lot going on inside the cell. It's not prokaryotic, it's eukaryotic. Another reason I picked it is because of the way that amoeba move. They extend pieces of their cell membrane out, like an arm or a foot reaching out. And at the end of that protrusion, there's receptors that are sampling the chemical nature of the neighborhood. And if what's in the neighborhood is good, the rest of the cell will be dragged behind and it'll move in that direction. And so the way that this cell appears, it would seem that it's kind of moving across the screen towards this end here. Okay. So there are big protrusions here called pseudopods moving out, and there are a few smaller pseudopods here, but most of the cell seems to be moving that direction. The reason I point this out is because this is very similar to how white blood cells move. And when we get to talking about white blood cells next week, I'll show you a movie of that, a couple of movies, actually. Just day before yesterday, one of my colleagues shared a link to this amazing video of a white blood cell moving like this. And I'm very excited to share that with my classes next week. So that's an amoeba. Multicellular parasites, multicellular organisms are represented here. Now, when I made this presentation, I was doing it over the summer one year. And in the summer when I teach from 8 to 12. Okay. And so after class was over at 12, I went to my office to do this. And I went to my office to do this while I was eating lunch. I did a Google search for parasitic worm. Okay. This is a warning. Never eat lunch and do Google searches for parasitic worm at the same time. This is the only picture that didn't disgust the hell out of me. Okay. But I love this picture. You can see in this the structure of this animal, this animal's tissues. So it has an epidermis, which is not exactly like our epidermis, but it has an outer covering. And then what you can see very well through the middle of this is smooth muscle that is its digestive tract. Okay. I'm not positive because it's a little bit out of focus, but I think this little dark spot here is a ganglion, which means that it's nervous tissue. And then some of the seemingly empty space in here is probably connective tissue. So this is an animal, okay? And when we're talking about multicellular parasites, we're usually talking about animals. Specifically, we're usually talking about worms. Now, so like I told you a little story, I was eating lunch, and this is the only one that didn't make me want to throw my lunch up. I have this other picture, which I did not find when I was eating lunch because of where I did find it. It's a little bit more disturbing picture, okay? This is a hookworm, okay? Now, a hookworm is another type of parasitic worm. I don't actually know what type of worm that was. I think that was a ringworm, but I'm not positive. Some sort of roundworm. But this is a hookworm, and we're looking down into its mouth. So these are teeth, not exactly like ours, but it's connective tissue making teeth. Obviously, it has a skin enclosing it. And then down into its gaping maw, we would eventually find a digestive tract, kind of like the worm we were just looking at. Okay. Now, there is a link at the bottom of this picture here. Actually, let me move this up. I'm not going to actually click on this version of the link because that link I actually have for you in Blackboard, which is this link right here. So if I clicked on the link that was on that picture, it would take us to this page right here. What I want to do with the rest of the time we have today is to listen to this podcast. Now, this website here is Radiolab, which is a show produced by WNYC, which is a public radio station in New York City. It is syndicated through the NPR networks, and I'm familiar with it because I used to listen to it on NPR all the time. When I was in school, I was down in North Carolina, and so the public radio station down there played it, I think it was Saturday afternoon or something like that. And I used to work out closer to Boston, and WBUR, whatever the NPR station is out in Boston, played it also, and I can't remember, it might have been Sunday morning or something like that. But, so I listened to it a lot. I don't know if it's played locally because I no longer listen to it on the radio. I just go directly to the podcast. Okay. So I listened to this podcast a while back, and it's actually a larger podcast. The whole thing is a podcast about parasites, which you're welcome to listen to the whole thing if you want to. But I just want to play part of it. So this is just a fragment of the podcast. The whole thing's about an hour long. This is about 23 or 24 minutes long. And I want to play this because I think it's a good little introduction to the pathogens that we're talking about and a little bit of the relationship between pathogens and immune function. So here's that picture I just showed you a second ago. The actual attribution of where it comes from is underneath if you're interested. And in the little blurb here, it kind of explains what this is going to go through. There's sort of two stories in this fragment of the podcast. The first one is about John D. Rockefeller and his attempts to expand his business model into the South and the importance of hookworm for that. And then the second half is about this guy named Jasper Lawrence, who has a very different relationship with hookworms than what's described in the first half. So I want to play this out, and while it's playing, because it's audio, there's no reason for us to stare at this page the whole time. I'm actually going to switch over to this page, and I'm going to write some things up on the screen if you'd like to keep up with sort of the notes I'm taking, just because there are certain things I want to highlight that are important to understanding immune system function in terms of what's going on here. So let me play this.
Hello, I'm Chad. I'm Rob. And I'm Robert Crowwood. This is
Oh.
Radiolab. Our topic today.
So, sorry, I meant to say this. So those two guys, they just introduced themselves, Jad Abramrod and Robert Krulwich. Jad is an employee of WNYC, and he's a sound engineer. He's a lot of why I really love this show, because he does a really good job of painting the picture with sound, so you really kind of understand what's going on. And part of what's going on here is going to be along those lines too. And then Robert Krulwich is the other reason I love this, because he's just a really cool guy. He's the science correspondent for NPR, but he's based in New York City. So this is sort of his regular gig. But if you listen to NPR, he's usually the person they interview for a lot of science stories. So.
Parasite. So we've met them, they're nice, and we've met them when they're not so nice. I don't know that we've met any nice ones, really. But we haven't? I thought that. Oh, yeah, they were nice. So, and now the question is to talk about the scale. I mean, for the most part, they're irritating and low, and they seem kind of invisible, sort of off stage. Yeah. But when we back off of it, they consider them, in the effects that they have on the world.
They're actually these powerful sculptors of monumental narrative.
In other words, these are little guys telling very big stories.
In fact, here's an example. Recently, I went to visit a guy named Dixon Desvantier from Columbia University. He's a paleontologist. Well, he has a bunch of different things. We ended up talking about, he told me this crazy story.
The story I love telling the most.
Oh, good. Before we start, I just want to say one thing. The following two stories contain moments that are a little bit gross. Just want to make sure you've been warned.
The story I love telling the most is how we eradicated hookworm.
The story begins in 1908.
John D. Rockefeller Sr.
This rich guy is sitting in his New York office. He's thinking,
How can I make more money selling something to the South?
yeah, I've got all this money, I've got all these resources. I just need a new market. In terms of new markets, the South is pretty much untapped. Only those damn Southerners.
You just get off their butts and get going.
Problem was, they weren't getting off their butts.
The farms were not operational. The economic engine was turned off.
The economy was in the toilet, and so John D. Rockefeller wanted to know why. Why aren't they producing more?
Yes. What's happened to their economic engine?
So he thought,
I know, I'll form a commission.
yeah,
So he sent out a bunch of economists and sociologists and people like that on the original Rockefeller Commission. They did everything a commission could possibly do to try to find out why these Southern gentlemen were not rising to the occasion. And they came back with the following conclusion. Well, we don't exactly know what they're doing, but we think that these people are sick from something because they don't behave like we do.
what does that mean?
They are slow, not mentally, they're slow physically, they're pale. I'll give you an example. Remember the movie Deliverance?
Or
Okay, remember that little guy that played the banjo?
I remember the other scene that we all remember.
Yeah,
We're not gonna talk about that.
No, we're not. If you could recall what that little banjo player looked like. A little wiry looking guy, but he looked old.
Sickly pale.
Yeah, sickly pale and yet an adult.
Well, wait a minute. That is not a description of all
all Southerners.
No, you're,
And
no,
one key corner in that.
no, but what the commission did say about a lot of these Southern people they encountered is that a lot of them, they just don't look right. They look weak, they look wan, they look kind of wan,
They were one.
pale, lethargic,
Interesting, whale or one?
wan. So the thought was that maybe these Southerners had some kind of laziness. Really what a lot of folks thought. The one around the committee suggested a rock, like, you know what, perhaps these people are anemic.
Anemic, they're anemic, you say? Yes, they're anemic. Sounds like a medical problem. Maybe they're not lazy after all, maybe they're anemic, maybe they're just weak.
Next thing you know, Rockefeller puts together another commission, this one with doctors, and he sends them back.
Back down to the south to find out what the basis for the anemia was. And not only did they find anemia, but they found a correlation of the anemia with soil types. Sandy loamy soils, anemia. Hard packed clay soils, sandy loamy soils, good farmland. Hard packed clay soils, not much good farmland. So all the rich farmers were anemic and all the poor farmers were doing okay.
And this seemed to be a clue. The incidence of anemia was linked somehow to the soil. Maybe, something was in the soil.
That's correct. So somehow they hit upon this idea of looking for hookworm.
The hookworm. So they thought, all right, let's run some tests.
When they did, big time, they discovered hookworm big time. So the anemia is due to hookworm.
Now the question became, how are these Southerners getting the hookworm, giving it to one another? And a pretty good place to start to look for an answer was their feces. Because if these hookworms are in you, they're going to come out of you when you go to the bathroom. So they asked these Southerners, when you guys defecate, where do you do it? Most of them said something like this.
And I defecate over there. See that tree over there? That's where I defecate. So I defecate over there, but I live over here.
Okay, so then the investigators asked the next question. When you go to that tree and do it, do you wear any shoes? Most of them said, no.
Barefoot, just like everybody else. Because it's comfortable.
So clearly these worms are in the feces that are landing near the tree, that are somehow getting into people's feet the next time they come to use the tree. But no one intentionally steps in their own, no one does that. Which meant,
Oh my goodness, it can crawl. Right, so let's find out how far it can crawl.
so what they did, these researchers, is they built a sandbox. Then they took some hookworm-infested stool.
And put it right in the middle. Then every day, we will sample from the stool sample out in the sand in all directions. Find larvae, find out how far they can crawl. Now we have larvae in the stool, and they begin to crawl away from the stool, seeking a victim. On day one, they crawled an entire foot in all directions, but they weren't at 2 feet. On day two, my God, they're at 2 feet. At day three, they're at 3 feet. I can't believe this. They're crawling a long way. Day four, they crawled at 4 feet.
What about day 5?
I'm allowed to ask. Okay. And what about day 5?
5 feet?
No.
No. 4 feet.
That's it.
So after 4 feet, they're what, exhausted?
One would assume on day 6, they were still at 4 feet. On day 7, they were dead. So how in the world could you deal with this problem when these worms can crawl? They can crawl 4 feet. It doesn't matter where you defecate. They're going to crawl away from that. And within a 4-foot radius of that stool sample, you're going to get hookworms. Unless you do something radical that's never been done before. They devised a scheme for burying the stool sample into the ground 6 feet deep.
Because if the worms can only make it 4 feet, well then that's 2 feet past the point where they die.
We call that the outhouse. So the outhouse was invented by exploring the life cycle of hookworms. And in fact, Rockefeller got his wish. The South did rise again.
That sounds too easy to me though. I mean, you're telling me that an understanding of hookworms created the outhouse, removed the quote, Southern laziness that they did rise. And you bring that all back to the hookworm?
I do.
Now, to be fair, you can find plenty of other reasons why the South rose again.
Air conditioning and highways and universities and stuff like that.
So Milgram had some help. But what is clear is that when we as a country began to distance ourselves from our own excrement, put it bluntly, when we stopped walking around in our own, there were all of these unintended consequences.
Salmonella disappeared, East Leviticus disappeared, Shigella disappeared, cholera disappeared, Giardia disappeared, Cryptosporidium, anything that's associated with parasites in feces disappeared. Every time we build outhouses and people use them religiously, guess what? Their kids can stay in school because they can learn more. They got ahead faster.
Dixon Desmamier is a professor of public health and environmental health sciences and microbiology at Columbia University.
Can they make longer titles in that university?
He literally wrote the book on parasites.
The book is called Parasitic Diseases. You know it very well. It's assumed to be a major motion picture, and now it's fourth edition.
In its fourth edition.
And while we're on the subject of hookworms and the glorious campaign to deworm America, because this has been a very carefully crafted and intentionally fair program, you have heard the case against hookworms. Now, let's turn the coin and say something nice about hookworms. And to begin that discussion, let's go to our reporter, Patrick Walters. So, Pat, are you there?
Yeah, I'm here, Robert.
So, tell us a little bit about this fellow. What's his name exactly?
His name is Jasper Lawrence. Jasper Lawrence.
So, where is he from?
He actually grew up in England. He grew up in this little farm in the southwest corner of England. And it's important to know, I think, before hearing any part of the story, that Jasper has had allergies for pretty much his whole life.
On really bad days, my eyes would swell up so much from pollen or airborne allergens that they would feel like they were swelling shut. I could feel my eyes squeaking in my sockets. It was an enormously uncomfortable feeling.
But it was nothing debilitating.
They were just allergies.
So, he's just like most other people with allergies, just learn to deal with it.
You live with it.
But
What changed for me in my late 20s, early 30s was my asthma. At that time, I was living in Santa Cruz. I was relatively recently married. We had 3 cats that had been grandfathered in with the relationship. And I started a landscaping business. I really didn't want to work for someone else.
I think someone with allergies starting a landscaping business, that seems kind of unexpected.
Stupid is actually the word for it. And within 6 months or a year, he starts to notice this really weird barking cough.
Was there anything particular that brought this on?
No, it was just sitting and breathing. Cats certainly didn't help.
Right.
And during that period, my asthma got much worse very, very quickly. By the time it was 1996, 1997, I was seeing specialists, having skin allergen tests and cycling through emergency inhalers, trying Singulair and all these other drugs that were coming on the market. I was being hospitalized at least a couple of times a year. I looked terrible. I had dark eyes and pale, waxy skin. I had that allergic look. It was a really bad time.
And he decides in the summer of 2004 to take a vacation. He made this visit to England.
Yeah, I took my 2 daughters back to see my aunt who had raised me. Very early in the visit, I was sitting at her kitchen table, and she asked me if I'd seen a BBC documentary about parasites in connection with things like asthma, allergies, and multiple sclerosis. And of course I hadn't. So I went upstairs and got on the internet after lunch, and I stayed on the internet until perhaps 2 in the morning. So
He's reading and
work all these research,
one study after the next.
Japan, and epidemiological studies in Africa, how enormous multiple sclerosis, this enormous weight of evidence.
That in the developing world, people don't really have asthma or allergies. And what he discovers is that behind all of this, to his shock, is hookworm. Hookworm? Yeah, hookworm.
Yeah, I learned that asthma was 50% less likely than someone who had a hookworm infection.
So this sort of just like hits you.
Oh, yeah.
What did you think when you read that?
Oh, I immediately was determined to obtain hookworm. Immediately. I couldn't wait.
So hookworms are these very tiny worms the size of a little hair. But if you take a microscope and you zoom way in, they have this big circular mouth brimming full of pointy teeth. Very scary to look at. They have these toothy mouths so that they can burrow up through your feet, right through your blood, and eventually end up down in your gut and start chewing on the inside of your intestines.
This guy wants bookworms in his intestines?
Absolutely. And so you just Google it?
Yeah, hookworms for sale. I mean, someone's got to be selling them. Nothing. I contacted every laboratory supply company in the world and parasitology research centers, and they all said the same thing. No, various flavors of no. And so I came to the conclusion that I was going to have to go to the tropics.
So fast forward a little. Defer's in Cameroon along the coast.
Quite literally, and figuratively, armpit of Africa.
It's 200 miles north of the equator. It's extremely hot. Find a guy, you drive him around. So he and his driver would go to a village, to get out of the car, walk up to these villagers, and ask them if they could see poetry.
Just an open area of ground, usually with bushes so people can have a little bit of privacy. And I would go over to the area, remove my shoes, and start walking. The first time I did that, I almost couldn't do it. It must have been 110 degrees that day, 100% humidity. And the stench and the noise from the insects, it was so repulsive and so disgusting.
How many villages or latrines do you think you visited?
Between 30 and 40.
Jasper spent 2 weeks there walking around in village latrines, and then he flew home.
And I got back from Africa in early February. So I was looking at allergy season coming up. And the day I realized that I no longer had allergies, that was such a good day. I got in my car and I started driving, and I had the window down. And I felt the breeze blowing across my face. In the past, what that meant was that very quickly my eyes would be itching uncontrollably, snot and phlegm was going to be pouring out of my face. And it didn't happen. It didn't happen. I just started screaming in the car. I was so happy. And I haven't had an asthma attack since I went to Africa. I no longer have allergies. The vast majority of the benefit that I've experienced has come from bookworm.
What is the hookworm doing? Do you know?
Well, so the immune system that we learn about in elementary school is all about like attack cells that go after foreign invaders and destroy them. And that's a big important part of the immune system. But if the immune system were allowed to attack and destroy things unchecked, it could kill you. And there are lots of diseases where the primary symptoms are caused by the immune system attacking the body that's really designed to protect. Allergies and asthma are just two of these. Some of the more serious ones are like type 1 diabetes, multiple sclerosis, Crohn's disease, which the immune system actually starts attacking the inside of the intestines. There are like 80 of these diseases. 80. And so what scientists have found in lots and lots of mouse studies, and in some human studies to this point too, is that once the hookworms get inside the gut and the immune system actually starts attacking, somehow hookworms actually stimulate these cells, which just quiet things down and tell the attack cells to stop attacking.
So these are like lullaby cells?
Exactly. What lots and lots of scientists think, Joel Watson,
Tufts Medical Center,
and dozens of others, is that over
thousands and thousands of years,
hookworms almost developed in tandem with the human immune system.
co-evolution, parasites taking body, your immune system changes.
You got to a point where hookworms can survive safely.
Worm gets up home, there's food coming down the food pipe, and in return,
The human immune system gains some kind of
some form of
positive regulatory
advantage.
so that if you had this glitch where your immune system started attacking your own body, the presence of the hookworms would keep things controlled.
And that's the gift. You do something for the worm does something for you. So that, by that logic, what we in the West, in the richer countries, have done stupidly is we have cleaned ourselves up too much and we don't have enough wormies in us.
Yeah, this is called
They call it the hygiene hypothesis. The hygiene hypothesis, that we're not dirty enough.
too clean.
We function like rainforests or ecosystems, and we've entirely eliminated a class of organisms that co-evolved with us and our genetic predecessors for millions of years.
Now, I don't want to leave the impression that hygiene is bad for you. People can't go back to living in filth, kids playing in sewage by the riverbank, but in improving our hygiene, there are also excluding organisms that may be important for man as well. So then what does Jasper do about all this?
He decides to start a business selling hookworm to people.
What?
You can call him up and he will literally FedEx a dose of hookworms to your door.
How?
Sorry, break it for a second. Pat,
Hi, Dad.
where does he get the hookworm from?
This is weird. Jasper gets the hookworm from himself. Could you describe how you go about getting hookworm from your stool into one of your patients?
Well, it's a very easy organism to work with. It gets up and it walks out of it. So it doesn't take an enormous amount of work to separate it from the species. And then having done that, I repeatedly wash them in solutions of antibiotics to make sure that anything that could live on them is killed. People contact us, we'll have them complete a questionnaire, submit a recent blood test, then we'll ship them a dose and all the materials and equipment and the instructions necessary to infect themselves.
Is this a safe thing to do?
Jasper has done tons and tons of research, but he's not a doctor. The treatment is not approved by the FDA.
That's what I wonder, is there any serious sort of double-blind study trying to figure out whether some safe delivery of hookworm might make sense?
Yes, and so one of the guys who was sort of a pioneer in this hookworm research is David Pritchard.
I'm Professor David Pritchard,
Immunologist and parasitologist.
at the University of Nottingham, where I study parasites and the wound-healing properties of maggots. So we've now got 2 safety trials under our belt, but we've yet to conduct the trials to show that therapeutic benefit results from infection with worms.
So Pritchard infected himself pretty much just to make sure that it was safe.
What we did was 10 of us in the lab took worms at different doses. We were either given 10, 25, 50 or 100 worms, and then we had to report on the symptoms. And on the back of that study, we determined that 10 worms were tolerated.
But Pritchard, when he did this proof of safety study, actually gave himself 50 hookworms, which been on commission for a while.
Well, I felt pretty bad. I mean, pain in the gut, really, you can feel them, but they are biting on your tissues.
I mean, if you have too many hookworms, they can cause things like diarrhea, and the most serious side effect, and the side effect that makes them sort of a public health enemy, is that they can give you anemia.
So if you have too many, you lose quite a bit of blood to these parasites.
Well, if you take too many hookworm, which you're not gonna, if you come to us, the worst thing you're gonna get is anemia. But it's not like you wake up one morning and you're drained of blood. Very slow to develop, and it's very easy to deal with.
Jasper's kind of just gone for it. It's a very sort of like cowboy move.
For the scientific community, I think they believe that I'm premature
It's not FDA approved.
in offering this to the public.
You don't know what it is, you don't know its purity, and it's not safe.
But I've talked to several clients who had really severe allergies and asthma. They say that they've just achieved these great results. Jasper also says he's seen success with a few multiple sclerosis patients and several Crohn's disease patients too. Like, how many people do you think that you have infected?
That's about 85 right now.
How is business? Is it everything that?
Business is adequate, but I honestly don't know why I don't wake up in the morning with my front garden 20 deep with people with ulcerative colitis, Crohn's disease, allergies. I just don't know why I'm not completely buried.
The way he sees it, people are scared.
Well, There are the people who are coming from a point of view of what they learned in kindergarten about clean drinking water and sewers. To them, worms and parasites are so repulsive that there's nothing good to be said about them. But I can make you better. It's simple, it's cheap. I mean, for God's sake, these organisms fall out my rear end every day, 500,000 at a time. The raw material is human excrement, for God's sake. All people have to do is open their minds. Are you really that scared of a little worm?
Okay, so the rest of the recording there is just sort of the credits and thank yous and all that sort of thing, which are important, and I don't want to discredit any contributions, but I don't want to use up class time to play through it. So I wrote a number of things here. If you didn't get this down, you can go to the recording, which will be on YouTube. This is actually the third class that I've done this recording in, and the other two, something went wrong with the recording. One of them, there was no audio or video. The second one, there was audio but no video. So I'm hoping this one shows that progression, and it'll have audio and video. So hopefully we'll see all of that there. Yeah.
So have been any steps toward FDA regulation ever been taken?
This recording comes from about 2008, and that's a question that everybody always has here. Me and students are always asking. So I did a little research. I don't know what Professor Pritchard's done since then. And I mean, as far as the FDA is concerned, he's in England, so he's not necessarily going to be doing it for the FDA. So I don't know if anything locally that's been done. But what I do know about the FDA's relationship to this, about 2010, Jasper Lawrence left the country. And the reason he left is kind of interesting and paints an interesting picture about the FDA's feelings about this. On a Friday afternoon, he got a call from the FDA saying, "Hey, Jasper, let's get together Monday morning and have a little talk." And he immediately packed up and drove south across the border. He lives in Santa Cruz or whatever. So he headed out of the country because he knew that that Monday morning talk was going to be him being served with a warrant or a fine or whatever for sort of breaking the FDA rules. So he just left because he knew there was no way for him to argue that this is good because the FDA was not interested in going that direction. I have not heard that there has been any FDA approval of this sort of approach, but and I don't anticipate that it would necessarily happen anytime soon. What he's saying there at the end, the kind of what you're scared of a worm sort of thing, really does illustrate probably the issue behind this, is that there's just an inertia that won't be overcome because, you know, part of the reason I liked playing this for you is because you folks get all grossed out when he's walking around and getting infected. And that's kind of the fun of doing this for you guys. But that attitude, people are going to say, hookworm, it's in poop. I'm not going to deal with it. So it's probably never going to be something that the FDA wants to approach. Just it's not in keeping with their ideals, I suppose. Just like they're not going to necessarily say, okay, let's go back to using leeches or something like that. It's gross and it smacks of unsanitary practices and that sort of thing. Now, the hygiene hypothesis basically says is that maybe those sanitary practices have gone a little too far. I've been playing this for my classes for a while, since probably 2009. And one semester, fairly recently, one of my students came up to me after class when I played this and said, you know, I have personal experience with this. Not that she has a hookworm infection necessarily, but she grew up in Mexico City. I didn't actually ask why she grew up in Mexico City. My sort of imagination, I imagine that like her parents were ambassadors and so she moved down there. But so she never came to America until she went to college at the age of 19. And I don't remember exactly where she said, and I think that ambassador fantasy that I have there is because I think she went to college in DC. But her first year at college, one of her dorm mates had really bad allergies. And she was convinced that her dorm mates were putting her on. She had never known anybody in her life that had allergies growing up in Mexico City. And it wasn't until she moved here, from what can be considered, as far as sanitary practices are concerned, a developing country, into the United States, where she first met people that were expressing what the hygiene hypothesis suggests happens, that those sort of sanitary practices can, in fact, cause problems. You've probably heard, when you go to Mexico, don't drink the water. If you've heard that, your probably first thought is, well, what do the people living there do? Why do they want to drink the water? People living there that do probably drink the water are immune to what's in the water. We're not immune to it because we don't live in that environment. And so those people, while they're immune to the things that will make United States travelers sick when they go down to Mexico, probably have low-grade infections of these sorts of things. In Mexico, they don't have, open latrines or anything like that, but they probably do have some sort of parasitic worm sort of situation going on thanks to the water supply or something like that. Yeah.
So usually, it's described mutualistic relationships. And usually, natural mutualistic relationships develop over a period of time. Usually, when you introduce an exotic species within an ecosystem, it basically exploits all the natural resources and overpopulates every normal flora that are normally there. So, I think this would maybe a little short-sighted that a longitudinal study is maybe needed to see what sort of,
I don't want to sit here and say, no, we should all go out there and get hooked on things. But what you're talking about, I understand where you're going with this. And what you're talking about, this mutualistic relationship, taking time over a long time, that's happened already for humans. Our immune system co-evolved with these types of organisms over hundreds of thousands of years. And it's only in the last 100 years, 200 years, whatever, that we've now gotten rid of those co-evolved organisms from our internal environment. So in places where that level of sanitation hasn't been introduced, those people are still living in that mutualistic relationship with the parasites. And it's in so-called developed countries where we're now seeing the consequence of eliminating that co-mutual organism from our system. And our immune system, which is supposed to exist with those things on board, now doesn't have anything to do. And that attack cell and lullaby cell thing is kind of getting at that without anything to actually fight off, attack cells will say, well, heck, that cell looks like fun, let's go kill it. And you get autoimmune diseases. The lullaby cells are the response to those baseline infections. When you don't have that baseline infection, the lullaby cells are not active and the attack cells are left to run rampant in your system, causing autoimmune disorders and allergies and that sort of thing. So that's the basis of the hypothesis, the hygiene hypothesis there.
The only question I was really having is just, even within a certain population groups, you have geographical speciation. It seems like certain populations already have this natural immunity. And, in Western cultures, we don't because of our sanitation practices. But, because that niche that resides, say, in Mexico City has this kind of already established in their environment. It's sub-evolutionary speciation could potentially occur, in that residents that have been there for a while.
Yeah. Certainly speciation can take place in a short time frame of 100 years or something like that. But for what we're talking about here, this is something that's been set up over, like I said, probably hundreds of thousands of years. So changes that are going to happen that quickly are not likely to be a big player in it. It's not like if we go out right now and get hookworm infestation from hookworms in Cameroon or something like that. That's not going to necessarily be problematic for us because we're geographically separated from Cameroon. Because of this mutual relationship between humans and parasitic worms, which is established over a very long time span, within 100 years, nothing's going to have changed enough to make that a significant difference. And Jasper Lawrence is a perfect example of that. And Pritchard's results are a perfect example of that. Okay, they're from different geographical locations, but they're dealing with the same kind of parasitic worms. And it's kind of interesting, down here at the bottom with Pritchard, it said, they did these trials and a small dosage, being exposed to 10 worms initially, is tolerated. No symptomology is seen there. Now, that doesn't mean that the person only has 10 worms. Those 10 worms are going to get into the intestinal system and make new worms, and some of those new worms are going to come out in the feces, and some of them are going to stay. So that infestation will grow. But when you start with 10 worms, your immune system can keep it under control. If you start with 50 worms, like he was actually in that group, he had intestinal cramps, he had probably some bleeding associated with it. And I'm sure that they would not have let it go to the point of anemia for any of these people, but if it were a natural infestation of about 50 worms, then anemia is probably going to happen down the road. And he wasn't even in the worst group. There's another group that got twice as many worms as him, so I can't imagine what their experience was. But so a limited exposure, which is what Jasper's says he does. He says if you follow my instructions, you're not going to get you're going to tolerate it. How I don't know, precise he is in that would satisfy an FDA protocol, that kind of thing, I can't say. And again, I'm not going to tell somebody to go out and get hookworms. Before 2012, there was actually a website where you go to and you could order hookworms for him. I think he still has a website, but I don't know if he actually ships hookworms out from wherever he lives now. I think he's back in England, but I'm not sure. But probably there's some customs law that will not allow him to ship hookworms into the country, thanks to whatever was getting the FDA agents to come visit him that time. But so I like this story because it does kind of make you think a little bit about our relationship with pathogens in our environment. And especially the Jasper Lawrence side of it shows you that it's not all about just fighting off infections and these attack cells that you talked about. But also we want to think about how the lack of certain pathogens might lead to some of the other kinds of immune responses that we see, like allergies and autoimmune disorders and that sort of thing. So next week we're going to look more specifically at what's happening in the immune response. And I want to kind of keep some of this in mind. And when I'm talking about that, I'm going to tell you what attack cells really are and what lullaby cells really are. So I'll refer back to this as we're talking about it. So if you don't have any other questions, that's it for today. Have a nice week.